Alright, so let's talk about distillation. So, the first thing that we need to talk about before we really get into it is VLE, just a basic reiteration of how vapor-liquid equilibrium works. So, the very first thing we're going to talk about is the idea of the XY diagram. So, we have our graph, we have Y, the gas phase, and X, liquid phase, and we put a 45-degree line down the middle of it. That means that X and Y are going to be equal across this line. So if I have X at 40, X being at 45%, I go up, it intersects Y, that's 45%. But that's not true VLE. True VLE is going to have some curve involved with it. So that means if I have X at, say, about 30%, and I go up here, after my flash, my vapor phase will be at, I don't know, whatever you'd call that, 75%. And so on and so forth. That's how these diagrams work. They are modeled by something called Raoult's law, which we have the mole fraction in the liquid phase times the vapor pressure in the liquid phase, or the vapor phase of that component, is going to equal our partial pressure of this component in the vapor phase, or the mole fraction times total pressure. You can find the vapor pressure using Anton's equation, but we're not going to go into that for the sake of this lecture. And then we have, okay, so this Raoult's law is useful for ideal components. Like, for example, if you're to have two components that have very similarly shaped molecules, such as 1 and 2 propanol, they're probably going to follow this Raoult's law very closely. But most vapor equilibrium binary mixtures aren't going to behave that way. So we can modify Raoult's law by adding in something we call the activity coefficient. So if we have xi, gamma I, and then the vapor pressure in the liquid. So this gamma I is called the activity coefficient. It is essentially a measurement of non-ideality in the liquid phase. And we're just going to set that equal to yi times p, partial pressure in the vapor phase. So this is Raoult's, and this is single modified Raoult's. When we do Raoult's law like this, we typically are going to modify in the liquid phase first, because non-idealities come from the fact that molecules will interact with each other. And since in a liquid the molecules are touching each other by definition of what a liquid is, we are going to modify that side first, and then we can have double modified Raoult's law as well, where we have xi, gamma I, p star I is going to equal yi, phi I, p. And that phi I is the fugacity coefficient. The activity coefficient and the fugacity coefficient are both measurements of non-ideality in the respective phases. When they're 1, that means the solution is ideal. When they're not 1, it means they deviate from the ideal. So I figure now that we have some background in play, we're going to, want to get into distillation itself. So let's say we're going to take a VLE. We're going to boil. So we're going to have our setup. We're going to have a boiling flask. We're going to have it in a mantle. We're going to have our liquid in there. And then we're going to have it hooked up to some kind of we're going to have it hooked up to where the vapors enter some kind of condenser. My pen is really not liking me right now. Condenser, it's going to have an exit spout. Oh, we're going to put a valve in it. It's going to have something, and then we're going to have the condenser up top with the, the balls to maximize surface area between the coolant liquid and the heating liquid, but that's besides the point. So what's going to happen is we're going to flash it. Whatever's going to come out is going to come out, and then we can collect the vapor. So if we have our XY diagram, right, we have exit 20%, we'll call right here. We're going to go up to the equilibrium point because that's all this is. We're reaching equilibrium. And then we're going to have Y at 50%. So this component at X, we're going to have 20% in the liquid phase. We flash it. Our collection right here is going to have that component at 50%, right? All right, so what if we collected a lot of that and we did it again, right? Well, that means we'll go on the BLE diagram, we'll go across, right, to the 45-degree line, because that's where Y is going to be the same as X. And remember, we just condensed this liquid, and we're going to flash it again. So this X is at approximately 50%. I know this is not the scale. We flash it, come over here. Now Y is at, I don't know, we'll call it 75%. And then, we'll intersect the 45, go down, flash it again, and so on and so forth. Now, this is the basic idea of what distillation is. Except in distillation, we're going to save a lot of energy by not having to condense it at each step. Alright, so in a distillation column, we're going to have our column. It's going to have many stages throughout. So I drew 8, I know it's again not to scale. And then we're going to have some form of boiler at the bottom. So for the sake of the argument, I'm just going to draw that boiling flask on a mantle again, put a liquid level in there. So what's going to happen here is the vapor is going to boil up the column, right? And up top we're also going to have a condenser, and I'll just draw it like they really are with little balls in there to maximize surface area between the cooling fluid and the vapor. So what's going to happen is the liquid's going to boil up through here, and we're going to have it condense, and it's either going to leave the column or we're going to come back down the column. That's called a reflux ratio. We'll get into that a little bit later. But for the sake of understanding what it is, we're going to talk about this now. So as this liquid is going to travel down the column, while the vapor is traveling up the column, we're going to have condensations on each of these trays. So each of these trays is going to be a single stage flash. Each of these trays is going to be a single staged flash like what we just talked about over here. And we're just going to be doing it multiple times in a row without the need of condensation because we have reflux to pull energy out of the system. And then down at the bottom, we can have a place for us to pull out bottom compositions as well. And we can also hook this back up to another reboiler that feeds back into the column or leaves the system, and this is called the boil-up ratio. Since the purpose of the reflux ratio is to increase, since the purpose of the reflux ratio is to remove energy from the system as well as create these multiple VLE stages on each tray, we'll talk about the purpose of the boil-up ratio. And the purpose of this boil-up ratio is to increase the amount of vapor that's going up the column. Increasing the amount of vapor going up the column is going to do several things, such as it's going to increase the amount of contact time between the liquid and the vapor on the trays and as they pass by each other. As they pass by each other, we're also going to see another effect that boosts the separation more so than just these multiple single stage flashes. As the liquid and the vapor pass by each other, I'll draw it out. So as the vapor is going up the column and as the liquid is going down the column, we're going to say we have components A and components B. Alright, so we're going to have component A and component B in this column. For the sake of the argument, we're going to assume that A is the more volatile, which means A is going to boil more readily than B in this mixture. And so these X and Y's are going to be in terms of the more volatile component A. So, as we're going up, we're going to have our mixture of A and B, and as we're going down as a liquid, we're going to have our binary mixture of A and B. What's going to happen as the liquid and the vapor pass each other between trays is there's going to be this thermal stripping effect. So the vapor, as it passes the liquid, is going to essentially vaporize the more volatile component using energy of condensation of the lesser volatile component. And vice versa, as the liquid's going down, it's going to condense the less volatile component and use that energy to vaporize the more volatile component in its stream. I think I just repeated myself, but it's kind of an important idea to understand. To reiterate, this is the vapor line, and this is the liquid. As the vapor's going up, the more volatile component is going to leave the liquid and go to the vapor. But that energy needs to come from somewhere, and that somewhere is going to come from the less volatile component in the vapor phase condensing and entering the liquid phase as they pass by each other. Alrighty. So now let's go into how we model this. We're going to do something called the McCabe Thiele method. So the McCabe Thiele method is a graphical method used to approximate the amount of stages we need. First, we're going to start with our XY diagram. We're going to have our 45-degree line, and we're going to have our vapor-liquid equilibrium curve. Right? The next line we're going to add is the Q line, and it's going to start at the feed composition with respect to X, hit the 45 degree, and it's going to come out at an angle that is going to be dependent on the feed conditions, and we'll get into that later. Our next line we're going to have is something called the stripping section operating line. What that's going to do is it's going to start at the bottoms composition. The bottoms is what's coming out of the boiling flask at the bottom of the column. Start at the 45-degree line, and it's going to go up and intersect the Q line. And lastly, we're going to have our rectifying section operating line, and what that's going to do is it's going to start at the distillate composition, so we'll call it distillate composition. This is the feed composition, and this is the bottoms composition. And what this is going to do is it's going to come and it's going to intersect the Q line, and these are all going to cross at the same point. So what we do here is, in order to count the stages, we're going to start at the operating line, we're going to go up and intersect equilibrium, and we're going to go back across. You always want to start and end on an operating line, and you're just going to go through until you're out of line, right? So see here, this is a partial stage, so we cannot count it. So that means we have 1, 2, 3 stages involved. Or if it makes you see it better, you can count on the operating lines, because that's where we actually hit them. So we're going to have 1, 2, 3 stages for the sake of this distillation. And that is how we use the McCabe-Thiele method to approximate the amount of stages we need. And again, in order to use this method, you're going to need to know what your bottoms composition is. You're going to need to know what you want your distillate composition to be. You're going to need to know your reflux ratio, and you're going to need to know your boil-up ratio before you begin. And we're about to get into that. So first things first, we're going to start with the rectifying section. Operating line. So, first thing we're going to do is we're going to do a mass balance about some stage in the rectifying section. The rectifying section means all stages above the feed stage. So, first thing we're going to do is we're going to have some stage in here. And this is a tray in the column, stage in. And so we're going to have liquid coming down as reflux, and we're going to have vapor coming up. And we're going to draw our next stage, which is going to be some stage n plus 1. Right? And we're going to have liquid coming down, vapor going up, and there can be an infinite number of stages above. We don't really know. And then we're going to have this top stage where our distillate D is going to come off, and again this is going to have liquid coming down and vapor coming up to it. And coming down here we're going to have liquid, vapor coming up. Below this stage N we're going to have some stage N minus 1, and then liquid going down, vapor coming up, and there can be some infinite number of stages before we reach our feed stage. So now we need to do our mass balance about N. First thing is we're going to name our compositions. So we're going to name these compositions using nomenclature that's telling us which stage it's going to. So if this is liquid coming down, it's going to be the liquid going to the nth stage, right? And if this is vapor coming up, it's going to be the vapor flow rate going to the nth stage. Here we're going to have the vapor flow rate going to the n plus 1 stage, and here we're going to have the liquid flow rate going to the n minus 1 stage. So if we do a mass balance about N, we're going to get that what's going into N, Ln plus Vn, is going to equal what's coming out of N, which is going to be Ln minus 1 plus Vn plus 1. So we also know that the distillate, what's going to this stage up here, this top stage, right here. So we know this is a fact, that based off this mass balance, we know that D is going to equal Vn plus 1, what we're sending up to it, minus whatever liquid's coming down from it, Ln. So if we take the mass balance and we put it in a form such that we can use this relationship, so if we rearrange our mass balance here, up here, then we can put it in a form where we can use this D term to simplify the equation. So we'll have Vn is going to equal Ln minus 1 plus Vn plus 1 minus Ln, right? And we know Vn plus 1 minus Ln is equal to D, so we have Vn is going to equal Ln minus 1 plus D, our distillate. Now, this is the mass balance, but again, with distillation, we're more interested in putting everything in terms of the more volatile component. So, our mole fraction of the vapor at stage N times Vn is going to equal our mole fraction about stage N minus 1, and then that's going to be plus the mole fraction of the more volatile component in the distillate stage times the distillate flow rate. So now we've put this all in terms of our more volatile component. Again, since we're doing a graph, we want this to be somewhat in terms of y equals mx plus b format. So we're going to have yn is going to equal L n minus 1 divided by Vn times x n minus 1 plus d over Vn times xd. Right, and remember, we have to kind of decide what we want that xd to be. So xn minus 1 is going to be the x value, yn is going to be the y value, d over Vn times xd is the intercept, and ln minus 1 over Vn is the slope. When we're doing McCabe-Thiele, we're assuming ideal distillation. And one of the assumptions we make is that the vapor flow rate is going to be constant. So our Vn equals Vn plus 1 equals Vn minus 1, etc., etc., and that's just going to equal V. And the same with our liquid flow rate. We're going to assume that Ln is going to equal Ln minus 1 is going to equal Ln plus 1 is going to equal L. So if we take this and we plug that assumption back into it, we're going to have the equation of the form Yn is going to equal L over V x n minus 1 plus d over V x d. And that cleans it up nicely. But how usable is this? It's very difficult for us to use. So what we want to do is we want to put it in terms of a user-friendly form, and we're going to do that by using our reflux ratio. So reflux ratio R is going to equal the liquid flow rate allowed back through the column, which is the reflux, divided by what we're pulling out of the top, L over D. So with this relationship in mind, we're going to rearrange L over V and D over V into something in terms of the reflux ratio, which is going to put it in a much more user-friendly form for us, because before we begin, we want to approximate what we want our reflux to be before we start. Now, remember over here, we got D equals V minus L. So with this in mind, we can say that V is going to equal D plus L, right? So first we're going to take this term, L over V, and we're going to rearrange it such that we have L divided by D plus L, using this relationship right here. Now, we're going to divide the top and the bottom by D. So we're going to multiply it by 1 over D divided by 1 over D. I am sure we all know how to do algebra by now. So that means we're going to be left with L over D divided by D over D plus L over D. And we just defined reflux ratio R as L over D. So that means this is equal to R divided by 1 plus R, the reflux ratio. So we're putting everything in terms of reflux ratio. Now, we're going to have D over V, and we're going to do the same thing. So we're going to turn D into V minus L, this relationship right here. So we're going to have V minus L over V, which is going to equal V over V minus L over V. Right? So that's going to equal 1 minus L over V. So up here, if you'll remember, we just turned L over V into R over 1 plus R. So that's going to equal 1 minus R over 1 plus R. This 1 is going to be equal to, because we want to put it all in terms of the same denominator so we could add them across, we're going to have, draw that with my little arrow, we're going to have R plus 1 over R plus 1 minus R over R plus 1 is going to equal, R's cancel out, 1 over R plus 1. So now, lastly, our rectifying section operating line is going to be in the form Y stage N is going to equal R divided by R plus 1 times X of the stage below plus 1 over R plus 1 times xt. That is our rectifying section operating line. Next, we're going to have to determine what our operating line for the stripping section is. So our stripping section operating line. So again, we're going to start with the mass balance about stage N. But remember, this time we're going down towards the bottoms. So we're going to have some liquid flow rate going down, some vapor flow rate going up, and we're going to have our stage N plus 1, and we're going to have our liquid going down and our vapor going up through an infinite number of stages, if we so desire, to some stage where we are going to be pulling off our bottoms composition. Same up here, and we're going to have our stage N minus 1, and we can have some infinite amount of stages before our feed stage. Now, because our feed is going to be different, or because our feed is going to change the flow rates up and down depending on if we're feeding in a vapor, liquid, or a mix of the two, we're going to signify the liquid and vapor flow rates with a different variable. They're still going to be L and V. The difference is we're going to put a little hat over them. And we're going to use the same nomenclature. So we're going to have some liquid stage going to N, and we're going to have some vapor stage going to N minus 1. And here we're going to have some liquid stage going to N plus 1, and here we're going to have some vapor stage going to N. And we're going to do the mass balance again. So we're going to get Ln plus Vn is going to equal Ln plus 1 minus Vn minus 1. Oh, plus Vn minus 1. And just like we did with the distillate, we're going to say that our bottoms flow rate is going to equal whatever liquid is going down into it minus whatever vapor is coming up from it. We're going to rearrange this so we can put B back into the equation. So we need Ln minus 1, or Ln plus 1 minus Vn. So we're going to rearrange this to say Ln is going to equal Vn minus 1 plus Ln plus 1 minus Vn, or Ln is going to equal Vn minus 1 plus B. So again, we're going to put everything in terms of our more volatile component because that's what we are the most interested in. So we're going to take the liquid mole fraction times the liquid. We're going to have the vapor mole fraction times the vapor. And we're going to have the bottoms mole fraction times the bottoms. Now again, McCabe Thiele's assumption is that everything is going to be constant above and below the feed stage. So that means that Ln is going to equal Ln minus 1. It's going to equal Ln plus 1. It's going to equal L hat. Same with the vapor. Vapor N is going to equal vapor N plus 1 minus vapor N minus 1. It's going to equal vapor hat. So we can rewrite our equation into Xn L equals Yn minus 1 V plus XB V. And we're also going to define our boil-up ratio. Boil-up ratio, and that's going to equal how much vapor we let back into the column divided by how much we're pulling out of the bottoms. Because remember, we can send it to a reboiler. So with this in mind, we're going to put this into our user-friendly form. We want it in a y equals mx plus b type form. So first we're going to divide everything by this v term. So we're going to have x n L over V is going to equal yn minus 1 plus xb v over v. So yn minus 1 equals xn L over v, put parentheses, minus xb v over v bar. Now it's time to do some algebra. So we're going to start with this L over v term, and we know from over here that b equals L minus v. So we know that L equals b plus v. So we're going to take that and plug it into this up here with this relationship. And so we're going to get b plus v bar divided by v bar, which is going to equal b over v bar plus 1. Right? And we defined boil-up ratio as v over b, so this is going to equal 1 over the boil-up ratio plus 1. And if this is equal to boil-up ratio over boil-up ratio, that means we're going to be left with boil-up ratio plus 1 divided by boil-up ratio. And that's what this L over V term is going to equal. Now, simple enough for this one, we have our B over V right here. And that's just going to equal 1 over the boil-up ratio. So now we are left with yn minus 1 equals the boil-up ratio plus 1 divided by the boil-up ratio times xn minus 1 over the boil-up ratio times xb. And again, when we're using McCabe Thiele, you want to know what that bottom's composition is going to be, and then you want to know what your boil-up ratio is, and you can get the slope of your operating line. So the last piece of the puzzle we have is the Q line. And as we said earlier, the slope of the Q line is going to be dependent on our feed stage. So essentially what we're trying to determine is how far are we going to be towards the rectifying section versus the stripping section. There's not much to write with respect to this other than the equation. Y is going to equal Q divided by Q minus 1 times X minus composition of the feed divided by Q minus 1. So the slope is going to be Q over Q minus 1. Now, Q is going to be based off of the feed. So if we're feeding as a just base, so we're going to draw our thing. Alright, so the slope of Q is the slope of the Q line is going to be Q over Q minus 1. But your value of Q is going to be dependent on how your feed is coming in. So if it's going to be a subcooled liquid, Q is going to be greater than 1. Right, and that's what we got over here on the far right of this diagram. Right here, subcooled liquid. And so if it's subcooled liquid, not only is it going to increase the liquid flow rate down in the stripping section, but it's also going to condense some of the vapor coming back up. And it's going to even more drastically increase our liquid flow rate down. So the line is shifted at an angle greater than that true 180 with coming straight up from the X line. And that's because our stripping section line is going to be much longer because we're going to be spending more time in the stripping section. If it is a saturated liquid where Q equals 1, that means we're at a liquid at its bubble point. This liquid is going to go down the column and it's going to increase the liquid flow rate, and means we're going to spend more time in the stripping section as well. If it's an even mix of liquid and vapor, we're going to have Q between 0 and 1. And what this means is the vapor in this flow rate, the vapor in that feed is going to go upwards in the column, and the liquid in that feed is going to go downwards in the column. And they're going to increase the flow rates, and we're going to assume that the amount of time spent in the stripping section and the rectifying section are about the same. If we have a saturated vapor, that means we're at a vapor at its bubble point. So as it comes in, it's going to start to condense. Well, as it comes in, it's going to increase the vapor flow rate up. And it's going to want to condense, so we don't have that drastic of a change. But initially that vapor is going to go up, so we're going to be spending more time in the rectifying section. And then if we have a superheated vapor, we're going to obviously be increasing the vapor flow rate up. But we are also going to vaporize some of our reflux that's coming back down and drastically increase that up, which means we're going to be spending a lot more time in the rectifying section. So if you combine all these things together, we get the stripping section line right here, blue. We get the Q line, the green, and then we get the red line, which is the rectifying section operating line. And that is how McCabe Thiele works.